Hi, and welcome to an introduction to waves. Here's a preview of this talk. What we're after is a mathematical description of electromagnetic wave phenomena. The way we're going to do this is by first talking about sound waves, which behave according to essentially the same math as EM waves, but are a little bit easier to understand. We'll end up with the wave equation, which turns out to be essentially the same wave equation that describes EM waves. Then we'll talk about the simplest non-trivial solution to the wave equation, namely a sinusoid, and explain some of the relevant properties. Finally, we'll talk about how, in terms of the mathematics, EM waves are different from sound waves. Now, before we get started, we need to be perfectly clear about something. Sound waves and electromagnetic waves are two completely distinct phenomena. Sound waves are variations in pressure, whereas electromagnetic waves are variations in electric and magnetic fields. However, it turns out that any one directional component of the electromagnetic field vector is governed by the same equation as for a sound wave, and we get this merely by changing the value of one single constant in the equation, as we'll soon see. Furthermore, sound waves are intuitive for most people because they are readily observed. So hopefully the mathematics will be easier to follow if I show you the sound case first. Okay, here we go. First, what is sound? Well, let's first define the absence of sound, that is silence. Silence is what you perceive when the air pressure is equal to its quiescent value, and that's about 101 kilopascals at sea level. For those not familiar with metric units, that's about 14.7 pounds per square inch. When you hear a tone, that's the air pressure varying sinusoidally around that quiescent value of the air pressure. So, a convenient mathematical description of sound is the differential pressure, that is, the difference between the absolute pressure and the quiescent value, which we'll assign the symbol P. Differential air pressure, P, is a function of time, of course, and that's what makes the tone possible to hear. But P is also a function of position. If we use Cartesian coordinates, we might refer to the position as a particular set of values for x, y, and z. So, P is a function of x, y, z, and also the time, t. Now, to simplify matters a bit, we'll limit ourselves to how P varies with just one of the three spatial coordinates, and here we'll choose x. That simplification is not going to change any of our findings, and when we're done, everything will generalize nicely to accommodate all three spatial coordinates. Let's start with the sound of a single clap. Before the clap happens, P equals 0 at all points in space. At time t equals 0, then this person claps their hands once. This forces the air between the hands to press outward, creating a region of increased pressure, that is, P greater than 0, and that region of increased pressure travels outward. As this region of increased pressure moves outward, it leaves behind a region of decreased pressure. Air molecules immediately move into this region of lower pressure, so the air pressure quickly returns to the quiescent value, that is, P equals 0. The time variation of pressure is not an instantaneous impulse, because interactions between air molecules constrain the pressure to vary continuously over space. So, instead of seeing pressure spikes, what we see is a rounded pulse representing the rapid buildup and similarly a rapid decline in air pressure, and then ultimately back to the quiescent value. The time at which you hear the clap depends on how far you are from the person who clapped. If you're close, you see this variation in air pressure at a relatively early time. If you're far away, it takes longer before you see this variation. At each point in time, you can make a plot of P, the differential pressure, versus x, the position, for the current value in time. For times t less than 0, we have, of course, simply P is equal to 0. A short time after t equals 0, the peak pressure is located slightly to the right of x equals 0, as is shown in the top plot on the right. A while later, P of x and t looks very similar, except the pulse is now further away, as in the bottom plot. Okay, so what precisely is this waveform, P of x and t? The answer is that P of x and t is the solution to the acoustic wave equation, which is shown here. This equation governs exactly how pressure may vary with space, that is x, and time, that is t. Now, there's all kinds of solutions for P from this equation, and the sound of the clap will be just one of them. In fact, we'll talk about a second solution, that is the tone, in just a moment. But the key idea is that whatever sound exists, that is, whatever function P we observe, it's going to be a solution to this equation. Now, the wave equation is a differential equation, but don't let that scare you. It's actually quite simple. All that's happening here is that there is a relationship between the rate at which P changes with space and the rate at which P changes with time. And that's it. The acoustic wave equation, that is the wave equation for sound, is simply a relationship between the rate at which P changes with space and the rate at which P changes with time. Now, you can fairly think of the wave equation as the thing which prevents the sound of the clap from appearing as an impulse simultaneously at all points in space, as opposed to what actually happens, which is a continuously varying waveform that propagates away from the clapping hands. So, what is this constant c sub s? Well, c sub s is the speed of sound, and that's about 340 meters per second at sea level. Now, it's tempting to think of c sub s as a speed, but in fact, it's a materials property. That is, the value of c sub s is determined by the fact that the sound is propagating in the air and not in some other substance like water or brick. Now, you may recognize from a previous lesson that we talked about the concept of phase velocity. And if you recognize c sub s as phase velocity for a sound wave, congratulations, that's 100% true, and we'll return to that idea in a moment. Okay, now the clap is an example of what we would refer to as a transient signal. And this means that from the perspective of an observer fixed at some point in space, the signal is not present before a certain time, and is also not present after a certain time. It's only present for a short period of time. For our purposes in understanding electromagnetic waves, a more useful signal of interest is the signal you get from a sinusoidally varying source, that is a tone. We can demonstrate the situation in the context of sound as well, and here we go. Let's say someone picks up a trumpet, and that person blows a perfect middle A note. The middle A is 440 hertz, that's 440 times per second, meaning that the air pressure emerging from the trumpet is varying sinusoidally at a frequency of 440 hertz. Now, let's say this musician continues to blow this note long enough for all of space to be filled with the sound of the trumpet. So in this case, what does the pressure versus distance curve look like? Well, two simple observations settle that question. First, at any constant position x, that is for someone located at some position x along the x-axis, p is just a sinusoidal function of t, having the same frequency as the source, that is 440 hertz. And this is because the wave equation describes a linear and time-invariant system. So a sinusoidal excitation, that is the trumpet, results in a sinusoidal response, that is the sound you hear, and it's at the same frequency. Now, at any given time, we can look at P of x and t as a function of x, and that's what's shown in the upper right of this slide. Again, we see a sinusoid, and this is because the sound is propagating away from the trumpet and toward the listener, so anyone in between will hear the A note, as we just established, but they'll hear it with a phase shift, and that phase shift is determined by the difference in distances. These two observations alone are enough to know that the function Px of t must have the general form shown here. That is, P of x and t equals some constant, called a sub m here, times the cosine of omega times t minus beta times x plus psi. Now, we don't quite know what the constants a sub m, beta, and psi are yet, but we are certain that the differential pressure has this form. Let's start with omega. Omega is simply 2 pi radians times the frequency f. Since frequency has units of 1 over seconds, the units of omega are radians per second. Because omega has units of angle over time, we call this angular frequency. But be clear, angular frequency is just another way of describing frequency. Just has different units. Now, what is beta? Well, note that beta plays precisely the same role for distance, that is x, as omega plays for time, that is t. Since beta multiplies x, it must have units of radians per meter, whereas omega had units of radians per second. For these reasons, beta is sometimes called spatial frequency, just like omega is angular frequency. More often, however, beta is referred to using terms like wavenumber or propagation constant, and these all mean essentially the same thing. So how do we get a value for beta? Well, one way we could figure this out would be to simply plug this expression for p of x and t into the wave equation and then solve for beta. And if you do this, and I highly recommend you do this on your own, it's straightforward, you will find that beta equals omega divided by c sub s. In fact, you can see right away that this gives us the correct units, that is radians per meter. In this particular problem, where f equals 440 hertz and c sub s equals 340 meters per second, you will find that beta equals 8.13 radians per meter. And you should make sure that you can calculate that number for yourself, 8.13 radians per meter. The fact that beta is 8.13 radians per meter means that at any given time, the difference in phase measured between any 2 points separated by distance of 1 meter is 8.13 radians. That's what it means for the propagation constant to be 8.13 radians per meter. Said differently, beta is the rate at which the phase of the sinusoidal wave progresses with distance, just as omega is the rate at which the phase of the sinusoidal wave progresses with time. And that's really all there is to it. In a previous lesson, we discussed the concept of wavelength, which is a distance between 2 points having equal phase, as shown in the figure at the top right, where it's shown as the symbol lambda. You may have already realized that beta and lambda must be giving us essentially the same information, and that's 100% correct. To see this clearly, just consider the little bit of math at the bottom of this slide. Beta is omega divided by c sub s, and omega is 2 pi times f. So, we have that beta equals 2 pi divided by lambda. And we see that it's true that beta and lambda are related by a constant, namely 2 pi. And so beta and lambda give us essentially the same information. A common source of anxiety about the solution to the wave equation is why beta should be accompanied by a minus sign. That is, why are we subtracting beta x? The idea here is that the sign of beta conveys the direction of propagation. That is, it indicates whether the wave is propagating in the plus x direction or the minus x direction. In other words, if the phase of the wave is increasing with beta x, then the wave is propagating in the plus x direction. If the phase of the wave is increasing with beta x, then the wave is propagating in the minus x direction. So, what does it mean that the wave travels in the minus x direction? Well, this will occur if you just happen to be to the left of the trumpet player, as shown in the bottom of the slide. Just imagine that the trumpet player is located at x equals 0. If you observe the wave from some location x greater than 0, then you see the wave with the minus sign in front of the beta. If, on the other hand, you observe the wave from some location x less than 0, then you see the wave with the plus sign in front of the beta. The sign tells you the direction in which a point of constant phase is moving. Now, let's be clear. At any point along the x-axis, the wave is traveling either toward the left or toward the right, and not in both directions, at least not in this problem. The wave equation is satisfied in either case, and the wave equation will not tell you which direction is correct. Here it takes a human, that means you, to figure out what sign to use. In other words, you have to bring some common sense to the problem in order to figure out whether it should be plus beta x or minus beta x. And now you should know how to make that choice. Alright, so now let's return to the topic of electromagnetic waves. What's going to be different for an EM wave relative to a sound wave? Well, let's look at the electric field intensity. Electric field intensity is a vector. In Cartesian form, we can think of the electric field as consisting of the sum of components, and these components point in the x, y, and z directions. That's what's shown in this expression underneath the first bullet. For example, let's consider the z-directed component, called E sub z in this expression. E sub z is a scalar function of x, y, z, and t, just like differential pressure is a scalar function of x, y, z, and t. The wave equation for E sub z is the same as the wave equation for differential pressure, with one critical difference. For EM, the phase velocity is not the speed of sound, that is c sub c, but rather the speed of electromagnetic radiation, which is just c. And c, of course, is commonly known as the speed of light. Now, that's in free space, so you know that phase velocity of an EM wave is less than c in other materials, so let's just say v sub p as opposed to c to avoid confusion later. And to be clear, v sub p, the phase velocity, equals c in free space, but is less than c in other media. Now, here's an essential idea. The other two components of E, that is Ex and Ey, as well as all three components of the magnetic field, B, all satisfy the same wave equation with the same phase velocity. That being the case, you might wonder why all six components of the electromagnetic field are not equal to each other. After all, if all six components satisfy the same wave equation, how can they be different? Well, the answer to that is that each component is subject to a different condition which is imposed by the source. So for example, in the sinusoidal wave example, the magnitude of each component and the phase of each component is determined by the magnitude, the phase, and the orientation of the source. So it's possible to have Ex be some non-zero value, whereas Ey and Ez might be equal to 0. The source determines how these values are going to be different. Now, you might wonder how we know that the six scalar components of an electromagnetic wave are all governed by the same wave equation, and how it is that we know that this particular wave equation is the one that I'm showing here on the right. Well, for the pressure wave that describes sound, simple physical considerations lead you to the wave equation. For electromagnetic waves, the relevant physical considerations are those embodied in Maxwell's equations, which are shown on the left side of this slide. Now, I'm not going to explain Maxwell's equations in this lesson, but for the purposes of this talk, there's really only one thing that you need to know, and that's this. Those upside-down deltas are derivatives with respect to space. And you see also derivatives with respect to time. If you attempt to combine all four of Maxwell's equations, you end up with the wave equation. It's just math. In fact, the same math that gets you from Maxwell's equations to the wave equation also tells us that the phase velocity is a materials parameter, and that phase velocity for an electromagnetic wave depends on the permittivity and the permeability of the material, and that in turn gives you the value for the speed of light. The rest of the explanation is just math. If you're interested in the derivation, and I hope you are, check out the reference at the bottom of the slide, or any other decent textbook on electromagnetics. Okay, time to sum up what we've learned. We've learned that all six spatial components of an EM wave individually satisfy the wave equation. We've learned that one possible solution to the wave equation is a sinusoid that varies as a function of both distance and time. But let's be clear, there are other possible solutions, and what specifically you get depends on the source. Remember, the trumpet gave us a propagating tone, but the clap gave us a very different, transient sound. and this analogy holds for EM as well. We have not yet considered how wave propagation varies with direction. That is, we've talked about propagation along the x-axis, but not propagation along the y or z-axes, or how these are related. Once we consider how waves propagate along various directions, we'll see that there are two really important types of waves, namely plane waves and spherical waves. And that concept will be covered in a future lesson. Also, we have not yet really explored what it means that the electromagnetic field is a vector. That is, what does it mean that the EM field has a direction at each point in space? Once we consider that, we'll see that this leads to the concept of polarization. That too will be covered in a future lesson. That concludes this introduction to waves. Thanks for listening.